This is what we did in the last class, Thevenin's and Norton's equivalent. Thevenin's equivalent of a circuit is a simplified version of a circuit that has a voltage source with a series resistance. Norton's equivalent of a circuit is also a simplified version of a circuit, but with a current source and a parallel resistance. Okay, but what is Thevenin's equivalent? What's the Thevenin's voltage? The idea of Thevenin's voltage that is defined. Thevenin's voltage is defined as the open circuit voltage. Okay, it's defined as the open circuit voltage between the two terminals of interest. That is when there is no current flowing through. Now, Norton's equivalent is defined as the short circuit current. We'll come back to talk about this a little bit more in today's class. But when you're calculating the Thevenin's equivalent, you open circuit the terminals A and B. While you're calculating the Norton's equivalent, you want to short circuit those two terminals and find the current. Okay, so Norton's equivalent, you find the current by short circuiting the terminals. Thevenin's equivalent, you find it by open circuiting these two terminals and looking at the voltage between them. That's all we did in the last class. In today's class, I want to talk about Thevenin's and Norton's equivalent when there are dependent current and voltage sources. But before we do that, I just want to spend a little bit more time working on a couple of examples. Let's see. So this guy, let's start with this guy. And the problem is that we want to find the Thevenin's equivalent of this guy. Okay, so in other words, I'm interested in finding this Thevenin's voltage and the Thevenin resistance. So what is R Thevenin? What is this V Thevenin? Okay, so that's the problem. Find out V Thevenin, find out the open circuit voltage, and find the Thevenin resistance. Okay, so let's solve this problem just to reinforce the concepts that we looked at yesterday. How do you find V Thevenin? Okay. The way to find V Thevenin is to apply the node voltage method. Okay. Let's apply the node voltage method to this circuit, the one on the top. Okay. In order to apply the node voltage method, the first step is to identify a ground node. I call that node as the ground node. Okay, I annotate that node as my ground node. And the next step is to identify some other independent nodes. Okay, so I'm going to call this V0. That's the node right there. I'm going to call this node as V1. Okay, and this guy as V2. Okay, and we know the value of V2 is 9 volts because it's being supplied by the 9-volt power supply. Okay. Let's see, When I'm interested in calculating Thevenin, that's this voltage I'm interested in finding. Okay, that's Thevenin. What's that value? Open circuit volt value. Okay, what's that value over there? So let's see if we can apply the node, voltage method to the different nodes here. Okay, so I'm going to write KCL at node V0. Okay, you think about it. If you want to add all the currents leaving the V0 node, there are three branches. Right? There are three branches. So there's a current going north, there's a current going west, and there's a current going south. So let's try to add them up. Okay, the current going north is V0. Okay, let's see, just give me 1 second. Okay, V0 minus 9 volts. So I'm looking at the current in this branch over there, V0 minus 9 volts by 20 ohms. Okay, plus the current going west is negative 1.8 amperes, plus the current going south is V0, okay, or VTH actually, that's VTH by 60 ohms. Okay, it's VTH by 60 ohms. Okay, now, or you can also write this guy, all of this equals to 0. Okay, negative 1.8 is the current going west. Current going south is V0 by 70 ohms. Does not matter. You can even do this, V0 by 70 ohms. Okay, the reason is this voltage V0, the current that is flowing through V0 has to pass through a series combination of 60 and 10 ohm resistances. So V0 by 70 ohms. That's the other current. Okay, so three nodes or three branches. So that's equation 1 for node voltage method KCL at V0. So let me see if I can apply KCL at the other node as well, which is this guy. Okay, so far we applied KCL at this node. Right? Let me color code them. Okay, let's see if I can apply KCL at that node V1 over there. Okay, if I apply KCL at node V1, okay, there are three currents, one current going west, another current going east, and a current going south. Okay, so let's account for those currents. KCL at node V1. Okay, when I write KCL at node V1, the current going west is V1 minus 9 volts over 5 ohms. Okay, and the current going south is V1 minus 0 over 25 ohms, and the current going east is 1.8 amperes. So let me see if I can incorporate those three into my equation. So V1 minus 9 volts by 5 ohms plus V1 over 25 ohms plus 1.8 all of that should equal 0. So there are two equations. Okay, what are the unknowns? I have V1 and V0 are my unknowns. So the unknowns are V1 and V0. Okay, so I should be able to get the values for V1 and VTH. Okay, so if you do that, from this equation here, V0, you'll get a value of V0 V0 to be 35 volts. Okay, so you'll get a value of V0 to be 35 volts. Okay, now let's see. It's this guy. Voltage here is 35 volts. So what would be VTH? VTH would be the voltage division between 60 and 10. So let me write the voltage division equation. Okay, VTH equals to 35 into 60 by 70. Okay, that is 60 plus 10, the voltage division, which implies that's equal to 30 volts. So Thevenin voltage, V Thevenin, equals to 30 volts. Okay, that's the first problem I wanted to solve. VTH equals to, what's the value of VTH? That's 30 volts. Now it's about finding R Thevenin. Okay, in order to find R Thevenin, let me copy this circuit. Copy that. Okay, paste it. I'm going to clean up all of this. Okay, let's see. I'm also going to crop this just so it's cropping. Okay, now on to finding part B, R Thevenin. How do you find R Thevenin? In order to find R Thevenin, remember we want to deactivate all independent sources. Okay, so let me first, what are the independent sources? There is one independent source over here. There is another source over there. So let me deactivate these sources by, how do you deactivate a current source? By open circuiting it. Okay, by open circuiting means you simply remove it from this circuit. Okay, how do you deactivate a voltage source? So you deactivated the current source over here. You also want to deactivate the voltage source. How do you do that? You do that by simply replacing the voltage source with a short. Okay, if you replace the voltage source with a short, that deactivates. That deactivates your voltage source. Now let's see if we can simplify this circuit. Okay? It's a matter of simplification. Now we don't have any independent sources. It's a really simple circuit here. Okay. Now, if you think about it, this parallel path and this parallel path, both of these paths are parallel. One path has a resistance of 0 ohms and one path has a resistance of 30 ohms. So the equivalent of these two parallel paths, the ones shown in green, is 0. So if I have to simplify this circuit, I'm going to end up with something that looks like so. 20 ohms on the top, okay? And I'm interested in finding the resistance that appears over here, 60 ohms. So I'm interested in finding the resistance looking in, okay, through these nodes. It's not 60, it's something in combination with 60, okay? Now, I'm going to replace the 20 ohms or the 25 and 5 ohms with a 0 because it's in parallel with 0 ohm resistance. So all I have here is another resistance, 10 ohms. So remember this guy is 30 in parallel with 0. So that is going to be 0. Okay, so I have 30 in parallel with 60. So if I simplify this circuit, I'm interested in finding the resistance looking in to this circuit. Okay, so what I find is one resistance, 60 ohms, and another resistance of 30 ohms. Okay, and what is the equivalent resistance looking into the circuit? So that's a parallel combination of 60 and 30, which should be 20 ohms. Okay, RTH therefore is 20 ohms, and V Thevenin, we found that its value is 30 volts. Okay, so we have the answer that we were after, the Thevenin's equivalent. Okay, so let me go back and fill in the value that I got. R Thevenin is after this number. I got a value of 20 ohms for this guy. Okay, and thus we found the Thevenin's equivalent circuit here. Questions, please. Questions so far?
I think I'm having a kind of a hard time seeing how 30 is in parallel with 0. I mean, I know it's true. I just like, as far as visualizing it, it's a little difficult.
Sure. This guy, how would you identify that they're in parallel? Look at where they're branching off. There are two paths. If you look at this green path here, okay, look at the green path and this path going south, okay? They're coming off of the same branch, okay? Let's see. They're coming off of the same node here, okay? That's where they're splitting into the right branch and the bottom branch, right? And look at where they're meeting. They're meeting back at the same point. Does that make sense? Do you see what I'm saying? So there are two paths. If you think of this, or in other words, going back to our analogy of cars, if you think of this as a big boulevard leading into two branches, okay, one going west and one going east, okay, all the cars, let's say there are 100 cars coming in, okay, and they have two paths to take. They could either go west or they could or go south, okay, and then they eventually merge back into this boulevard over here, okay. So they originate in the purple path at the top. They split up into two roads which are parallel to each other, which go off and meet back at two different nodes. and then
Okay.
the current, the rows. You see what I'm saying?
I do. Yeah, that makes a lot more sense. Thank you.
Okay, okay, of course, of course. So there are two parallel paths here, 30 in parallel with 0. So all the cars that are flowing here would take the 0 resistance path. Or in other words, there is absolutely no voltage drop or current drop in the other path. 30 is in parallel with 0. Okay. Other questions, please. Okay. All right. So let's continue there. Okay, that's better. I'll leave it there. Now, so once we do that, I have a value of R Thevenin and also V Thevenin. Okay, in order to I understand the idea of Norton's equivalent circuit and the interrelationship between Thevenin's and Norton's equivalent currents. Let's see if we can solve the exact same problem by Norton's equivalent. Find the Norton equivalent for this circuit. So in other words, I'm interested in finding this guy. A current source with a resistance in parallel. Okay. What's the value of R Thevenin? And what's the value of I Norton? Okay. R Thevenin, we found this in the previous problem to be 20 ohms. So we don't have to redo the problem. Even if we did, we'll go through the exact same step, exact same numbers, and arrive at this exact same answer, R Thevenin, because the process is identical. Now it's about finding I Norton. Okay. What is I Norton? Okay. I Norton is short circuit current. Short circuit current. So in other words, if you have to find the I Norton between terminals A and B, what you do is to short these two terminals, A and B, okay, and look at the current flowing in there, I Norton. Okay, that's the definition for the Norton's current, right? So how do you find the Norton's current? That's how you would find it. Now, what observation can you make about what happens when you short this current, when you short these two terminals A and B?
There should no longer be a voltage across the 60 ohm resistor.
Correct, exactly. So there's no voltage across the 60 ohm resistance, and it's almost like there is no resistance over there. That's because all the current that is coming in here, okay, all the current that's coming in here is going to flow through this branch, and there is no current that is flowing in this branch because this 60 is in parallel with 0. Short is a 0, right? So the equivalent resistance of 60 and 0 short is that it's a 0. Okay, so this is what we have. Okay, so this 60 ohm resistance is eliminated from the circuit. Okay, so let me redraw this circuit just so it's easy for me to do the analysis. Okay, so there is this 20 ohm resistance, 5 ohm, 25, 10, some current, 1.8 amperes, and there is this guy. Okay, and then the voltage source plus minus 9 volts. Okay, I'm interested in finding the current I Norton. So this is 10 ohms, 25 ohms, okay, 5 ohms, and 20 ohms, okay. This is 1.8 amperes. So how do you find the Norton's equivalent? So what you do is to write the KVL, okay. So at this node, let's call this V2, okay. At node V2, this is ground. Let's call this guy as ground, okay. Node V2, let's write KCL. Okay, let's write KCL at node V2. There are 3 currents leaving. There's one going this way, there's another going this way. There's another current I Norton going south. So if I were to do that, V2 over 10 ohms, that's the current going south, which is I Norton, plus negative 1.8 amperes, that's the current going west, plus the current going in the upper branch, 20 ohm branch, is V2 minus 9 volts by 20 ohms. All of that equals to 0, which should give you a value of V2 to be, will give you a value of V2 to be 15 volts, from which you should be able to calculate I Norton. Okay, remember this part is I Norton. Okay, the current going south, that guy is V2 minus 0 over 10 amperes or over 10 ohms. That's the Norton current, I Norton. Okay, so I Norton is, so this guy, all of this guy equals to I Norton. Okay, so I Norton is V2 over 10 ohms. Now that you know the value of V2 to be 15 volts, you have a value of I Norton to be 1.5 amperes. Okay, so I Norton is 1.5 amperes and R Thevenin is 20 ohms. Questions, please. Okay, so let's quickly recap. For the same circuit on the top, if I did the Thevenin's equivalent, okay, I came up with something like this, plus minus 30 volts, with a series resistance of 20 ohms. This is the Thevenin's equivalent. Similarly, if you were to do the Norton's equivalent, you have a current source of 1.5 amperes, okay, with a resistance in parallel. The value of the resistance is 20 ohms, okay. So the one on the left is the Thevenin's equivalent. The one on the right is Norton's equivalent. Okay, so the idea is that if you source transform this voltage source with a series resistance by dividing VTH 30 by 20, you can go back and forth between these two. They're interchangeable. Okay, so that's something I want you to look at. And that's also a confirmation for you that your Thevenin and I Norton, this is I Norton and Thevenin are consistent, and proof positive that you did the problem correctly. Questions, please. So we looked at two problems in finding the Thevenin's equivalent and Norton's equivalent when there are independent sources. Okay. Now let's see what we do when there are dependent sources. What should we do if there are dependent sources? Okay. Something like this. How do you find the Thevenin's equivalent of a circuit when you have a dependent voltage or current source? Okay. How do you do that? This is where I'm going to introduce a new technique to you. Okay. The idea is that we cannot directly find the value for our Thevenin. So we are going to have to apply a test voltage and test current. Okay. So in order to find our Thevenin, I define our Thevenin as the applied test voltage over the observed test current. Okay, V test over I test. So this is a new technique. This is applicable when there are dependent voltage and current sources. Okay, so here is the idea. In order to find R Thevenin, you can apply, you can find that out by V Thevenin over I Norton, or the other technique is to apply a test voltage, okay, to the terminals of a circuit and look at the test current. Divide the test voltage by the test current. Okay, and I want to illustrate that using an example here. Let's see, just give me 1 second. Okay, let's see if we can find the Thevenin's equivalent of this guy. Copy that. Right here. It's already here for me. Copy. So the idea is find the Thevenin's equivalent of the circuit. Okay, in order to find the Thevenin's equivalent of the circuit, there are two things I need to do. I need to find the VAB, which is defined as V Thevenin or the open circuit. Okay, the second problem is to find R Thevenin. What is the resistance looking into these terminals? Okay, what is VAB? That's problem A. Okay, what's problem? So in order to find, okay, so let's start by finding, observing that VAB equals to VTH. Okay, VAB equals to VTH. Okay, now the current flowing IX is 0. The current flowing in here, IX is 0. Okay, and then let's start by writing the expression for I, current I, flowing in the top left branch, 2 kilo ohm resistance. Okay, so I, first step, okay, is to write the expression for I. The current going I is 5 volts minus 3V. It's not volts, but it's 3 variable V, right? 3V. over 2 kilo ohms. Okay, so I get an equation from here, 5 minus 3 times V equals to 2000 I. So I get an equation here. And of course, I know that Ix equals to 0. Okay, now the next step is to write KCL at node. Let me call this as node. Okay, I'll call this as node VTH. Okay, so I want to write KCL at node VTH. Okay, there are two currents. There is one current going west and a current going south. Okay, the current going west is 20 times I. Okay, the current going west is 20 times I plus the current going south is V Thevenin or VTH, which is the same as V. Okay, the voltage applied there, or the voltage across the 25 ohm resistance by the 25 ohms, all of that should equal 0. So this is my second equation, which tells me that 500, if I rewrite this, 500 times I plus VTH equals to 0. So this is my second equation. Okay, but VTH is the same as V, right? So I'm going to simply call this as V. Okay, because VTH, remember, VTH and V are the exact same potential across the 25 ohm resistance. Okay, which is same as V as well, VAB as well. So I have two equations. The one right here, one in two variables, little v and I, and the second equation, little v and I. So I should be able to calculate the value for v. Okay, I should be able to calculate the value of little I to be 0.01 amperes and little v, which is the same as the V threshold, V Thevenin, okay, V Thevenin, you get a value of negative 5 volts. Okay, if you plug in V equals to I equals to 0.01, you get a value of V Thevenin equals to negative 5 volts. That's straightforward. So far, we did not still apply the test voltage method. Okay, so how about finding RTH? How do you find RTH here? Okay, in order to find RTH, what you have to do is to apply the test voltage, test current. Okay, let's see if I can apply a test voltage, test current to this circuit. Okay, just give me a second. Okay, for this circuit, let me copy this. We have to find the VThevenin. We sure did find the value of VThevenin to be minus 5 volts. So what remains is to find the RThevenin. So let's find the RThevenin here. So finding RThevenin, using test voltage, test current method. V test, I test. Okay. It's not straightforward to find the value for R Thevenin just by deactivating the voltage source. Earlier, we deactivated the voltage source, and that simplified the circuit to not have any more sources, right? But that's not the case here. Even when I deactivate this voltage source, there are still some dependent sources that are intact. And so I simply cannot apply the deactivation method alone. That's not enough. Still have to do that, but that's not enough. So what I do is an interesting technique of applying a hypothetical test voltage. Okay, I'm going to apply a test voltage, V test, and look at the current going in, I test. So if I can calculate V test over I test, let me call this as test. Okay, that gives me the current looking in, which is the R Thevenin. Okay, so let's see if we can do that. In order to do that, notice that on the extreme left here, I started by deactivating, okay, or short circuiting the voltage source here. I deactivated the voltage source here. So the first step is to deactivate all independent voltage sources and current sources. I deactivated all the independent sources. Now, the next step is to apply KCL on the right-hand side equation at this node, okay, at that node over here. If I apply KCL at that node, let's apply KCL at that node, we'll see that there are three currents leaving. There's one current going west, there's one current going south, and there's one current going east. Three currents in three branches. Okay, so let's see if we can set that up. The current going left, current going to the left is V test, or I'm sorry, the current going left is simply 20I. Okay, the westbound current is 20I, and the current going south is V test because that's the voltage I'm applying at that node over 25. Okay, that's the current going south. Okay, plus what's the current going east? The current going east is simply negative I test. All of that equals to 0. Okay, apply KCL at node, call this as V test. Or I don't know, I can call this as V. We'll simply call this as node 1 at node 1. Okay, and you apply KCL at node 1. That is what you would get. And from Ohm's law, see, you're not interested in negative 3VT over. Now, you know the value for, you know the expression for I, remember? The expression for I was?
It was 5 minus 3 over 2 kilo ohms.
5 minus 3 over 2 kilo ohms. In here, I got rid of 5, so it's simply 0 minus 3 little v over 2 kilo ohms. Okay, so what I have is negative 3 little v over 2000. That's I. That's my second equation. Okay, so what I'm trying to do is simply get an expression. Okay, now what I can do is to manipulate all of these equations. Okay, let me see. This V is the same as this V. So V equals to V Thevenin. All right. Now, so if I am to write these two equations, okay, if I have to write the two equations, the equation one on the top and the one on the bottom together, I get something like this. Okay.
Professor, did you
Negative
mean V Thevenin or V test?
V test. Thank you. Thank you. I did mean V test. Okay. So now I'm going to plug in this 20 times I is negative 3 V test over 2000. Okay, that's because this I value is negative 3 V test over 2000. I'm going to plug it back in here, plus V test over 25. So that's this guy, okay, minus I test equals to 0. So I end up with one equation. Okay, I end up with one equation, and there are two unknowns. So there's no way for me to find the value for these two unknowns over here. Okay, so let me rearrange this a little bit more. So I can write this equation to appear something like so. If I factor out V test, okay, if I factor V test out, I get something like this. Excuse me. Okay, if I
Bless you.
factor V test, thank you. I'm going to be left with 1 over 25 minus 60 over 2000 minus I test equals to 0, or simply this guy equals to that guy. Okay, so the idea being here, there's no easy way for me, and there's absolutely no way for me, forget about easy or difficult, there's no way for me to find the value of V test or I test. But fortunately, I don't care about the particular value of V test or the value of I test. All I care about is this guy, V test over I test, which simply is 1 over 25 minus 60 over 2000 in the denominator. Okay, so if you solve that, this guy is R Thevenin. R Thevenin will come out to a value of 100 ohms. Okay, so that's the idea of finding R Thevenin using test voltage and test current method. Let me go back and review what I did. Okay, if you're asked to calculate, so finding R Thevenin using R test, we found out R Thevenin to be 100 ohms. Okay, so what I did was to, if you have a bunch of dependent sources, finding the Thevenin voltage, V Thevenin, is still the same. Okay, you apply KCL at a node of interest, you set up the constraint equation, and then you get a value for V Thevenin to be negative 5 volts. That's the first part. The second part is finding R Thevenin. Okay, you start by deactivating the independent voltage source. In this figure, it's on the extreme left. I replaced it with a short. Okay, now the part that is different so far is in this problem is that we have to apply a hypothetical test voltage V test and look at the resulting I test. Okay, now in order to find R Thevenin, you simply get an expression, massage the equation to find V test over I test. Okay, so you set up KCL at node 1. Okay, 20I V test over 25. That's one equation. The second equation comes from the left-hand side, where I is 0 minus 3 volts by 2K. So you set up two equations. There are three unknowns here, so two equations won't be enough. You are left with one big equation that has two unknowns. Okay, you don't need the particular values of these unknowns, V test and I test. You just want a ratio of these two. So you rearrange the equation to get a value for V test over I test, which comes out to be 100 volts, 100 ohms. So that's how you'd find the Thevenin's equivalent. Okay, let's see Thevenin's equivalent. So let's do one more problem. Let's do one more problem to really make this thing clear. Let's see if I have the problem up here. Yes, let's do this problem. Find the Thevenin equivalent of the circuit with respect to terminals A and B shown. Okay, so the first step, as always, and I have not shown this step explicitly in the previous stages, is to identify the ground terminal. And I'm going to call this node, that guy, as some V Thevenin. And I'm interested in finding this guy, V Thevenin. Okay, and of course, R Thevenin. How do you find V Thevenin and how do you find R Thevenin? Okay, let's see if we can start by finding V Thevenin. Okay, the first thing I'm going to do is to write KCL, so solution. We are interested in finding V Thevenin and R Thevenin. Okay, in order to find V Thevenin, let's start by writing KCL at node. I don't want to call this V Thevenin. I'll call this node 1, just so it's clear, crystal clear, as to what I'm talking about. KCL at node 1. There are how many? There are a bunch of currents here. There is one current going west. There's one current going north, a current going south, and a current going in this direction. So there's a current going in the eastward direction. So there are four currents at node 1. Let's see if we can add them up. Okay, the current going left through the 2 ohm resistance is V1 or V Thevenin. That's the voltage over there, right? V Thevenin. That's the voltage across at that node V Thevenin, which is the same as this node. Both of these nodes are the same, right? So V Thevenin minus 24 volts by 2 ohms. That's the current going west, plus what's the current going south? 4 amperes, plus the current going north and left is 3 times Ix, plus the current going in this direction, which eventually goes south, but the current eastbound is Ix, which is the same as all of that equals 0. Okay, that's one expression. But from the same circuit, from the same figure, I can notice that the current going here, Ix, is actually VTH over 8 ohms. Okay, so Ix, that's the current going in the 8 ohm resistance, is V Thevenin, that's the voltage across these two terminals, the 8 ohm resistance over the resistance, 8 ohms. Okay, that's so from this, by solving these two equations together, okay, we can get a value for V Thevenin to be 8 volts. Okay, there are two equations and two unknowns, Ix and VTH are the unknowns, and you have two equations. So we should be able to calculate the value for V Thevenin to be 8 ohms, 8 volts. Okay, but the interesting part is in finding R Thevenin. Let's see if we can do that. Let me copy this. Okay, and I'm going to paste it over here. Clean this up a little bit. Okay, we found V Thevenin, all right. We found V Thevenin to be 8 volts. Okay, and now next step is to find R Thevenin. What is the value of R Thevenin? By noticing that there is a dependent voltage source, we have to use test voltage, test current method. Okay, what's this first step in the test voltage, test current method? The first step is to deactivate this voltage source. Okay, we deactivate this voltage source and apply a test voltage here. Okay, I apply a test voltage plus minus V test, and I apply the test voltage at the terminal of interest to me. If I want to find the R Thevenin looking into these two terminals, then I apply the test voltage at that two terminals, I test. Okay, and all of this is to find the value for R Thevenin. Okay, so I apply a test voltage and I look at the test current. Okay, let's see, and I'm going to still call this node, okay, which is the same as this node, as node 1. Okay, so at node 1. So when we apply the test voltage, the natural step is to apply KCL at node 1. Okay, we notice that there are 1, 2, 3, 4, 5 currents. Okay, there are 5 different currents. I'm going to show them using this color over here. Okay, so when I set up my KCL equation, I'm going to see that there are 5 different terms in my KCL. Okay, so let's see if I can write the KCL equation over here. And by the way, did I forget to do something? What did I forget to do?
We have to remove the current.
Thank you. I have to remove the current source, and that's what I'm going to do. Here you go. Okay. I have to deactivate the current source, right? And that's what I did. Now, when I'm finding the test voltage, test current method, let me see voltage at V1, node V1. At node V1, V test minus 0 over 8 ohms. That's the current Ix. Okay, the current Ix. Okay, The current going south is V test, or V. I'm going to use them as a short form. VT is a short form for V test. Okay, so V test minus 0 over 8 ohms is the same as IX. Okay, so when I write KCL at let's see. So this is one equation. This is, let me call this equation number 1. So when I write KCL at node 1, there are 1, 2, 3, 4 branch currents. Let me see if I can add them up. The current going in the west branch, 2 ohm resistance, is V1, or V test minus 0 over 2 ohms. That's the current going left. Plus, there's a current going north, which is given to be 3 times IX. Okay, and there's a current going south, which is given to be 1 times IX. Okay, this guy 1 times IX. Okay, IX. Okay, that's the current going south. And what's the current going east? The current going east is negative I test. All of that is 0. Okay, so now what I can do is to plug in V test over 8 ohms in place of this guy. Okay, I can plug in V test over 8 ohms in place of this guy. Okay, so I can massage these equations and see that this is going to come out to be, V test over 1 by 2 ohms plus, see this 4 IX, all of that I can write it as V test over 2. So when I factor out V test, it's going to be 1 over 2 ohms. Okay, plus 3 over 8 over 1 over 8. So all of that equals to I test. Okay, I'm not interested in calculating V test or I test per se. I'm interested in calculating V test over I test, which is going to come out to be 1/2 plus 1/2 inverted, which is 1 ohm. Okay, therefore the Thevenin's equivalent resistance, RTH, that's the definition, right? RTH is V test over I test, which has come out to be 1 ohm. Okay, now R Thevenin is 1 ohm. So if I go back to the problem, I found V Thevenin to be 8 volts. Okay, and R Thevenin to be 1 ohm. Okay, V Thevenin and R Thevenin. How did I find R Thevenin? By applying a test voltage, test current method. And then it's a matter of simplifying these equations. Write or in other words, apply a test voltage, test current, and set up KCL. Questions, please. Okay, so this is how you find V Thevenin and R Thevenin when you're out to calculate using the test voltage, test current method. Practice some more problems. If you notice, all the steps involved here so far, all the techniques using finding the Thevenin's equivalent, finding the Norton's equivalent, or source transformation, all of these are simply application of the techniques that we learned so far, like KCL, setting up KCL, Ohm's law. And that's about it. Source transformation, so on and so forth. Okay. So even when I say that the Thevenin's equivalent or the Norton's equivalent are new circuit solution techniques, as much as they are new techniques, what you want to realize is that they're just manifestation of KCL and KVL. Okay. See, notice that I'm simply applying the exact same thing, KCL at a particular node, constraint equation. So these are all topics and techniques that we are very comfortable with already. Does that make sense?
Yes.
Questions, please. Okay. Let's see. Let's go back and revisit the list of techniques that we started building in the beginning of chapter 4. We did cover quite a bit of ground. So we added 3 techniques: source transformation, Thevenin's equivalent, and Norton's equivalent. Let's see if we did anything else. Source transformations, Thevenin's equivalent, Norton's equivalent. Okay, so we already looked at node voltage method and mesh current method. Okay, so let me scroll all the way back up to where I started building a list of techniques. Sorry about the not the best way of navigating all the way to the top. Okay, right here. Okay, I gave you 8 techniques, starting with the passive sign convention, KCL, KVL, series and parallel simplification, current division, voltage division. We saw how to use MATLAB to solve simultaneous equations for us. We saw the node voltage and mesh current method. Now we looked at source transformations. Okay, and then we looked at Thevenin's equivalent. And of course, Norton's equivalent. And how do you find R Thevenin using V-test, I-test method? Okay, so these are the new techniques that we picked up so far. Let's see if the converted text tool is any good. Cool. Accepting a few 7 minutes. Okay, Thevenin's equivalent, of course, and then Norton's equivalent using RTH, using V-test and I-test. So I'm impressed with the tool. That's good. Okay, but here are the techniques that we learned so far. Okay, so now let's see what else we have to do. So we are almost towards the tail end of chapter 4. Let me do a better way here. So chapter 4, as you can see, is the lengthiest and most extensive set of tools. It's the lengthiest chapter so far and in this course. So we did actually cover a lot of ground here. There are a couple more topics, okay? Maximum power transfer theorem, okay? And superposition theorem, okay? These are the only two topics that are remaining. I'm going to just talk about them, introduce them in a very informal way. And then I don't want to overwhelm you with a whole lot of topics on the same day. Okay, so I'll just introduce you to these topics and then um, talk about them in more detail in the next class. Okay, let's say you have a voltage source and then there's a load. So there's a load, there's a source, and there's a resistance associated with the source. So this is source resistance. Okay, so the idea of maximum power transfer theorem, okay, the maximum power is delivered from the source to the load because the load is where you want the maximum amount of power delivered to. Okay, so if that is your goal, the maximum power transfer theorem says maximum power is delivered when the source resistance here is matched to the load resistance. It's called resistance matching or impedance matching. That's all there is to power transfer theorem. And most oftentimes, it will be your goal to maximize the power delivered to the load resistance. So think of this as the, the total power that is generated in the voltage source, some of that is dropped off in the source and some of that comes out as a load. Okay, you want a whole lot of that power to come out to the load. Okay, and in order to do that, in order to make sure that you get a lot of power from the source to the load, okay, you want to make sure that the impedance of the source and the impedance of the load match. Okay, that's all there is to that maximum power transfer theorem. Okay, let's see. There is proof of this. I'm not going to go into the proof of this. All there is about the proof is to look at the derivative of this and equate that derivative to 0. Okay, in order to find the maximum or minimum, you have to equate the first order derivative to 0. That represents the inflection point or the maximum or minimum point. Okay, the conclusion is of importance to us. Okay, the maximum power is delivered to the load RL when R Thevenin or the source resistance is equals to the load resistance, and that is of consequence and that is of importance to us, this conclusion. Okay, that's all there is to the idea of maximum power transfer theorem. And the idea of superposition is, let's see, there are two independent sources here, right? Now, in order to simplify the analysis of the circuit, what we can do, the idea of superposition is I can break this circuit into two equivalent circuits. Okay, pay careful attention to what I'm doing here. The first thing I'm going to do is to deactivate one of the current sources. Okay, I'm going to leave this voltage source intact. Okay, I'm going to leave the voltage source intact and deactivate the current source. Okay, let's see, find the value V in here. Okay, I'm interested in calculating the voltage. Oops, I'm interested in calculating the voltage here, V. Okay, in order to calculate the voltage V, what I'm going to do is to simplify this circuit into two different circuits. Okay, simplify this circuit into two different circuits. In the second circuit, I'm going to leave the current source intact, but deactivate the voltage source. How do you deactivate the voltage source? By short circuiting it. Okay, but I leave the current source intact. Okay, so there is 5 ohms over here, there is 2 ohms, 10 ohms, and 12 ohms. Okay, so the idea is, let me call this voltage in the absence of the current source as V dash. Okay, and I'll call this voltage in the absence of the voltage source as V double dash. Okay, superposition theorem says okay, you can add, okay, this is a really neat characteristic of linear circuits. You can add the behavior of the top circuit and the behavior of the bottom circuit to get the effective behavior of the overall circuit. So in other words, by superposition theorem, okay, the value that you're interested in finding, V, can be found out by using V dash and V double dash. Okay, if you think about it, if I go back to the circuit over here, doing this circuit is really straightforward, isn't it? So it's just one voltage source and a bunch of resistors. I can use a voltage division carefully to do that. Okay, here finding the voltage across this 10 ohm resistance V double dash is also easy because there's only one source and a bunch of resistors. I can use a current division method. Okay, now once I find V dash and I find V double dash, then I can evaluate the overall behavior of the circuit V, which is the sum of V dash and V double dash. Okay, let me color code this using purple, pink. Okay, I'm going to color code this as pink as well. Okay, so that's the idea. So in other words, in formal terms, the idea of superposition is that the total response of a system is the sum of all the responses from each independent source when applied independently. Okay, and that translates to building two different circuits, the one on the top with the current source deactivated and the one on the bottom shown in blue with the voltage source deactivated. When you add them up, you get the voltage of interest to you, overall response. Does that make sense?
Yes.
So what I want to do is to leave this as a little bit of an exercise for you to go through these problems. The problems have been solved for you. Okay, so go through these problems and see if there are if there's any part of it that you don't understand. But I do want to leave this as an exercise for you. So let me go all the way back and add to the list of tools that we already discussed, the different tool sets. Okay, there is that guy right here. Okay, so let me add superposition. Okay. 13. Maximum power transfer theorem. And of course, the superposition theorem. So these are the different techniques that we covered. And with this, we finish all the topics that we want to cover in chapter number 14. As you can see, chapter number 4, as you can see, this is a very lengthy, long chapter, chapter number 4, but it does give you quite a number of 14 different tools to simplify, analyze the circuit. Okay, so after you take this course, after you finish this course, all of these should be second nature to you. How do you apply KCL? How do you apply KVL? Series parallel simplification, current division, voltage division, the node voltage method, mesh current, so on and so forth. All of these techniques should become second nature to you. Okay, superposition theorem simply states if you can evaluate the response of a system to individual sources separately, you can add them up later to get the overall response. The maximum power transfer theorem says you want to match the impedance of the source to the load, and that is the condition under which the maximum power is delivered to the load. Okay, so I want to leave it as an exercise for you to read through this chapter, read through number 13 and 14. I did talk about this in principle, okay, but I do want you to spend some time going through them, going through some example problems. Okay, so today is the 28th. So we did cover the maximum power transfer, test voltage, test current method, and of course, also the superposition theorem. Okay, when we come back, we look at ideal operational amplifier. It's not a big chapter. It only takes a couple of days, but that's I think that it's a muddiest point in the chapter. Okay, in the course. Okay, if there is one chapter that is the muddiest, that's the most confusing to wrap our head around, it's chapter number 5, operational amplifiers. Okay, I'll try my best to make things as simple as possible, as clear as possible, but there is a little bit of a leap of understanding that we have to take here, quantum leap in understanding in order to understand ideal op-amp. It appears like a quantum understanding, but once you get the hang of it, it becomes second nature to you. But at the end of the day, it's again the same techniques, the 14, 15 techniques that I gave you earlier. You see them being applied over and over and over again, even when it comes to chapter number 5. Okay, so the seminal, most important list of techniques is given in chapter 4. Once you master them, chapter 5 becomes extremely easy. And I'm going to be walking through a bunch of different problems, a number of problems in chapter 5, just so it takes the mysticism out of it. So it's not we'll demystify this chapter, operational amplifiers. Okay, so we'll come back tomorrow 8 o'clock and then start chapter 5. Questions, please. All right, we'll stop here. We'll see you folks tomorrow.
Thank you.